In the previous video, we explored why no single performance metric can fully describe how well a hydrological model performs. And we introduced 10 commonly used metrics, each capturing a different aspect of the hydrograph. But understanding the theory is only part of the story. In this video, we take the next step and bring all those metrics into practice, calculating them step by step in Excel and applying them to a simulated hydrograph. Well, our example is a 30-day hydrograph. You can see the observed versus simulated here. Generally, we start with the visual inspection. We have a dedicated video about it. That's generally our first step. I invite you to watch that if you haven't yet. As you can see, the low flows have been simulated relatively good. The peak is a bit early and it is underestimated. Generally, we can see that a big part of the hydrograph is underestimating, while the low flow values are overestimated. Now we want to see what numerical performance metrics are going to tell us about this hydrograph. I need to have some preparation here in Excel. First one is error, the simulated minus observed value. After that, the absolute value of it. Then, because of the log transform needed for the Log-NSE, I need to have the ln of observed Q and the ln of simulated Q. And then we have a bit of calculation here related to NSE and RMSE. In column J and K, the calculation that I have is basically the observed minus the average observed value squared. And then column K is the error squared. And then L and M are basically the similar calculation of J and K, but for the log transform scenario. So for example, here, what I'm doing is the ln observed minus the average ln observed. And here is the difference between the ln of observed and simulated value with the power of 2. So let's start the calculation. I start with the error. It's very simple. It will be the simulated value minus the observed one. And then I'm going to drag it down. And after that, I'm using the absolute function in Excel in order to find the absolute value. Drag it down. Then ln, I'm using the ln function, natural logarithm, and that will be for the observed and will be dragged down. Same thing for the simulated value. And then drag it down. And now let's move to columns J to M. For that, I need the average value. So I scroll down here. I've already calculated the summation, maximum, average, and standard deviation of these columns. And now I come back to start. Here, the value will be the observed one minus the average observed, which is this value. And don't forget to put $sign in order to fix it, because this is the number that we don't want to change when we drag it down. And then that goes down to here. Okay, now column K. So here we are going to have basically the error power 2. So what you can do simply is giving this one a power of 2, and that's it. Then we move to the log transform. So for this one, what I have is basically the ln of the observed minus the average value of it, which is this one with the $sign. And of course, a power of 2. Drag it down. And then the last one is the difference between observed and simulated log transform values with the power of 2, which will be dragged down. Now we are ready to start the calculation of the performance metrics. First, we go for NSE. This is the formula that we had. So it's very simple. Basically, what I'm going to do, I need the summation of the error squared and also the difference between observed and the average one. Basically, column J and K, I need the summation of them. So what I'm going to do here, I just drag this. So these are the 4 values that I'm going to use. Give it a yellow color. Now we calculate the NSE. So it will be 1 minus the summation of column K divided by summation of column J. And that's it. So we get 0.92. So same thing for Log-NSE. That will be simple. So it's just similar to NSE, but the log value. So for me will be 1 minus the summation of column M divided by summation of column L. And that will be 0.949. So as you can see, and as it was expected, the performance in the low flows are relatively better as visually we inspected earlier. Now we move to KGE. KGE has 3 parameters, R, alpha, and beta, that I need to calculate. So I start with the R, which is the simplest one. That's the correlation coefficient. So basically you can use the correl function in Excel, and that is going to be between observed value and the simulated one. And that's it. The next one, alpha, is the variability ratio, which will be the ratio of the standard deviation of the simulated and the observed values. So that simply means I need to divide this value by this one. So I get 0.78. And then parameter beta, which is the bias ratio. So that will be simply the ratio of the average values, or the mean basically, of the simulated over observed. And that's it. So my initial judgment based on the values that I've got, it seems the overall correlation is good. The mean value is also relatively very close to each other. But when it comes to the variability or alpha, we see that there is a bit of difference between the standard deviation, and that is related to this underestimation or overestimation that are happening here. So now we are ready to calculate the KGE based on these values. So that will be 1 minus the square root of R minus 1 squared plus alpha minus 1 squared, and finally beta minus 1 squared. And then we close the bracket. So the KG is 0.761. So as you can see, compared to NSE, it is penalizing this underestimation a bit better than NSE. So something that is missing because of perhaps the lag effect or the delay, which is not captured well by NSE, is nicely captured by KGE. So then we move to R square. That will be simple. R square is basically the R value with power of 2. So that also gives a very high number, but we know that that's not true. That's not really the case here. Then we move to RMSE, which is quite simple. As you can see, it's basically the square root of average squared error. So SQRT of the average square root. So square root is here, column K. The average value of that is calculated like this. So I get 12.445. And remember that this has a unit, cubic meter per second. And if you remember in our earlier discussion, we mentioned that it's really hard to understand whether this is a good number or a bad number. In order to have a better understanding of what is happening here, it is always recommended to use the normalized value of that. And we can do the normalization by using different ways. So one of the normalization methods was based on the mean value. So simply I divide the RMSE value that I just found by the value of average observed. And that gives me 0.24. If you want to look at it as a percentage, that means 24%. So now you have a bit of understanding. So RMSE that we have found here is relatively 24% of the average values available in Hydrograph. So that means that it is relatively a big error. So it's not something that we can ignore. When it comes to MAE, the situation is easier. It's mean absolute error. We have a absolute error column here, column F, and the mean value of that is already calculated, and that's 8. So remember, RMSE generally is larger than MAE, and if you see the difference is relatively big, that means that you have either underestimation or overestimation, which is the case in our hydrograph. Then we move to PBIAS. So here we just need to be careful about the definitions here. So basically it is the summation of errors divided by the summation of observed, but we noted that the error has been calculated as observed minus simulated. So this is basically the opposite sign of what we have in column E. So that's why here when I start the calculation, I need to multiply to a negative sign of the summation of the errors that I've got here. And then I divide it by the summation of observed value. So we noted that PBIAS has a sign. So a positive value means the observed is larger than simulated, or in other words, we have underestimation, as this is the case for us. And if you get a negative one, that means that you have overestimation, and it is coming by percentage. So basically from the value point of view, PBIAS of 9.3% is not bad. It's good actually. So we are not expecting a huge volume error here based on the PBIAS calculation. Now let's move to VE. This is also another volume error. It gives the exact same value that we got from PBIAS, but with an opposite sign. So here we get 100 multiplies to bracket open summation of simulated values minus summation of observed values, close the bracket, divided by observed. And that's what I get. So in VE case, basically negative means underestimation and positive means overestimation. Now we move to peak flow bias. It's simple. Basically we are after the difference between the simulated and observed peak flow divided by observed ones. So I have the values ready here. It will be 100 multiplies to the maximum simulated value minus the observed one. Of course, I need to have brackets and then divide it by the observed value, the observed peak. And that will give me 13.175. A negative sign means underestimation, and 13.1 is percentage basically. TPE is also important. It's the error in time. And generally what we need to do is locating the peaks that we have already found. So I show it by giving it a color. So this is the simulated peak and this is my observed peak. And as you can see, there is a 1 day difference between them. So basically, if you want to just write it, the time to peak in the simulated one is 11 and in the other one is 12. So that means we have minus 1 day early peak. The key takeaways from this example are as follows. First, NSE and R² can still give misleadingly high values despite under or overestimation or significant timing errors. Second, KGE is more reliable than NSE and R². Third, we may still get reasonably good volume errors in PBIAS or VE, while the estimated peak or overall hydrograph shape is unsatisfactory. Fourth, it is always better to work with normalized RMSE than the standard one to have a better sense of the error scale. Also, note that comparing MAE and RMSE can give us more insight into error propagation across the hydrograph. As you saw, performance assessment in hydrological modeling is multidimensional, and using multiple metrics is not optional, it's necessary. If you found this helpful, stay tuned. There's a lot more coming on practical hydrological modeling. Thank you for watching. See you in the next one.